Hello, and welcome to this Eureka webinar in association with Maxon. My name is Paul Fanning, and I'm editor of Eureka. Today's presentation is entitled How to Get Maximum Performance from a Brushless DC Motor, and it's being presented by Matthew Dean, Medical Sales Engineer for Maxon. I'll hand over to Matthew shortly, but before I do, I'd just say that if you have any questions during the presentation, please type them into the box on the right-hand side of your screen, and we'll attempt to answer them at the end. If we don't have time for your questions, we will hand them all on to Maxon, and they will answer them for you offline. And with that, it just remains for me to hand over to Matt. Matt, take it away.
Thank you very much, Paul. Right, let's make a start. I'd like to introduce you to Maxon. So the slide you're looking at here is of Swiss Lake, and on the right hand side is the Maxon factory. Maxon has been making motors since the early 60s, and the location of the factory is right next to Lake Sarnen, which is geographically right in the center of Switzerland. So we make around 5 million motors a year, about 16,000 different variations. We have 3,000 employees worldwide, and we have all the core competencies you would expect from a world-leading motor manufacturer, including winding technology, gearbox manufacturing, encoder and sensor technology and manufacturing, drive electronics, injection molding, including ceramic and metal, system integration, and mechatronics. So in a nutshell, that's who Maxon is. So this presentation is all about getting the maximum performance from a brushless DC motor. So let's start by looking at what we typically see inside the motor. So this is the exploded view, and there's a couple of components that I'd like to highlight. First of all, item number 6, which is the rotor. Now, within that rotor is a permanent magnet, typically a one-pole pair magnet. So it's got a north pole and a south pole, and that is rotated, that is fixed to the shaft, which is item number 6, and that is the rotating part inside the motor and delivers the power. Item number 4, you can see there is the coil. That is the Maxon special winding. It's a winding that is self-supporting, so it's not wound around anything. It's a cylinder of copper winding, and that lives inside the motor housing, which is identified as item number 2. The key component that I'd like you to look at on this slide is item number 3, which is the laminated steel stack. And that is the part of the motor where the magnetic circuit flows through from the rotor, which is item number 5. Those are the basic key components inside a brushless DC motor. So if we take that motor and we hold it in our hand and we cross-section it, so we're now looking down through a cross-section of the motor. If we start from the outside, you can see the motor case, then the steel laminations, then the winding phases or the coil, the Hall sensors, and the magnetic rotor. In this case, it's a one-pole pair with a north and south pole. And running right through the center of the motor, you can see the shaft. So if we now look at the circuits that are going on inside the motor, there's more than one circuit. You've got the electrical circuit powering the Hall sensors. You've got the electrical circuit, which is the current flowing through the winding. You've got the magnetic circuit coming from the winding, and you've got the magnetic circuit from the permanent magnet, which is the rotor inside the magnet. What I've drawn on this diagram is the magnetic flux, which is the black lines, showing the path that they flow through the steel stack. And this is really where a lot of the focus of this presentation is going to be, is on these magnetic flux lines. So this is a little bit more detailed drawing, but essentially we're looking at the same thing, which is the cross section of the motor. And there's two red circles that I've highlighted where the magnetic flux becomes concentrated inside the motor. So the red part and the green part is the north and south pole of the rotor. And you can see the magnetic flux lines flowing through the steel laminations or magnetic return. And the thickness of the magnetic return I've just called T. And you can see that where the two poles meet on the rotor, where the red part meets the green part, that is where the magnetic flux becomes much more dense. And that is the highlighted area by those red circles. The important thing to note here is that if we increase the magnetic flux, or we use a more powerful magnet, and we don't allow the magnetic flux to flow through the concentrated area, or there isn't enough metal or material for the magnetic flux to flow, then you won't get everything out of the magnet. You basically restrict what the magnet can do. It's the same as putting a resistor in an electrical circuit. So you must make sure that your magnetic return or steel stack is thick enough to handle all the magnetic flux coming from the permanent magnet in the motor rotor. So everything I've talked about so far has been a one-pole pair rotor or permanent magnet in the rotor, which is shown on the left-hand side of this slide. You have a north and a south, pretty simple. A four-pole motor, what the four-pole is really referring to is the motor rotor. So on the right-hand side, you can see the four-pole rotor. So you have two norths and two souths. The picture in the middle is just a little cross section where you can see inside the motor, and you can see the quadrants which make, or the magnet quadrants which make up the rotor. That's what those arrows are indicating. So why would you do that? Why would you go from a one-pole pair motor to a two-pole pair? And the answer is, it's to do with the areas where the magnetic flux becomes concentrated. So if you can see on the diagram here, we now have four areas where the flux is magnified. Shall we say there's four areas where the magnetic flux can become concentrated. If we look to the right part of the picture, what you'll see is the difference, the main fundamental difference between the four-pole motor, which is on the far right, and the middle motor, which is in the center, is the steel stack, or where the magnetic circuit flows. You can make it thinner with the four-pole motor, and you can do that because you have more saturation. You have four areas sharing the load path of the magnetic circuit. So why would you do that? What does that do for you? Well, if we make the steel stack thinner by going to four poles, it frees up space inside the motor. What you can do is you can start filling that free space with things which will result in a higher power density from the motor. So you can use a thicker coil. So in this case, what I'm showing you here is the maxon knitted winding. So if we want to wind the special coil using thicker wire, you can only do that by having a knitted winding. So you wind the coil in sections and then you knit the sections together to make the 360-degree coil. The other thing it does for you is, because we've made the stack thinner, we can increase the diameter of the rotor. If we increase the diameter of the rotor, we get more torque. Force times distance. So we've increased the distance, we'll get more force, more torque from the motor. So if we compare a typical one-pole pair motor and we compare it to a two-pole pair motor or a four-pole motor, you can see the difference in performance. So both of these motors are 30 mil in diameter and they're both 64 mil long. They've got the same outer case. But the difference is, if you look at the nominal torque, the four-pole motor, which is the motor on the right, is able to produce around 50% more torque. Not only that, but you can have a bigger shaft running through the motor, and you can use bigger bearings. So that is a fundamental difference and a big step up in terms of performance when going to the four-pole motor. Is there a downside? Well, unfortunately, there is a downside. First of all, cost. It's more expensive to manufacture the four-pole motor. Typically, it uses more expensive materials and components, and also it's far more complicated to make the knitted winding than the traditional maxon winding. Another downside is the electronics, which commutate the motor or drive the motor. The commutation needs to happen twice as fast in order to get the same speed out the motor. So your drive electronics have to work harder. And for high speed applications, speeds of 30,000 RPM upwards, we would suggest a one-pole pair motor is used. In fact, all of Maxon's latest ECX range, which are generally high-speed motors, they're all one-pole pair. So if we now look at an application where maybe we need a gearbox. So we've got this four-pole motor, which is the highest performing motor, and we need to couple it to a gearbox. Now, there are many different types of gearboxes using different types of gearbox technology that you can couple it to. But what if you wanted to match the four-pole motor performance and use the equivalent gearbox, which uses the latest materials and design techniques in order to get the most out of the motor? So here on this slide, I'm showing you the range, the typical range of Maxon's gearboxes. They're all planetary, range designed, each one designed for a specific job, whether it be low noise, reduced backlash, very high speeds, or high power in terms of torque. But the highest performing gearbox is the ultra performance. Shown there is the GPX UP range. That, coupled to the four-pole motor, makes the highest possible power density from a motor and gearbox package. Now let's have a little look inside this ultra performance gearbox and we'll see what's going on. One of the big differences in the UP gearbox is the planetary gears are all running on needle roller bearings. So in most planetary gearboxes, what you'll find is the planetary gears are running on a fixed surface, whether it's a ceramic pin or whether it's a steel pin. In the UP gearbox, they're now running on roller bearings. What does this do for you? Well, lowers friction, so you get higher gearbox efficiency, and low wear, longer life. And the gearbox is no longer limited by the PV value or pressure stroke velocity value between the gear bore and the pin axle that the gear is running on. That typically is the weakest link in a gearbox. Also within the UP gearbox, you'll find machined annulus gears or ring gears. So they're not sintered, they're machined to higher tolerances. Same with the planetary gears, machined, not sintered. And parts where normally they would be made out of two parts, pressed together, then welded together, they may be machined as a single component. All this results in tighter tolerances, and the use of the needle roller bearings does a number of things, but it also reduces backlash in the gearbox. So typical planetary gearbox might have 1 to 1.4 degrees of backlash. In the UP gearbox, that drops down to 0.3 to 0.4 of a degree, and an increase in gearbox efficiency. Instead of running typically about 75%, we're now up to 96%. But highlighted in red here is a key point. For similar sized gearboxes, the continuous torque can be almost doubled from the UP gearbox compared to the more traditional planetary gearbox construction. So we now have the highest power density motor, which is the 4-pole motor, and the UP gearbox, the ultra performance gearbox. So as a package, it delivers the highest power density. You've got low backlash, zero cogging, which is a nature of Maxon's winding in the brushless motor, low noise, and extreme designs are possible with this type of technology, whether it's got to handle huge variations in temperature, vibration, shock. That could be space or aerospace type applications, but also medical applications where you really need often the highest power density power transmission component in order to do what you want to do. So there we are. That's my little presentation, and these are my contact details. So I'll hand over to Paul.
Thanks very much, Matt. That was great. We now have a little time for some questions. We have some here. And if I could start perhaps with this one for you. What are the typical sizes of the 4-pole and UP gearboxes?
Okay, typical sizes at the minute for the 4-pole motor, 22 mil OD and 30 mil OD. So it's right in the middle of Maxon's brushless motor range. And I expect this range will grow both smaller and bigger in the coming years.
Okay. And this one now, if you can go from 2-pole to 4-pole, can you just keep on increasing the number of poles?
You can, but what it becomes a sort of law of diminishing returns. If you went to, let's say, 8-pole motor, it would be hugely more complicated to manufacture, and it wouldn't give you very much more in terms of performance. Some of our motors, or many of our motors in our catalogue, have got higher poles, 8 upwards, but they use different winding technology, so that they starts introducing cogging, which is not really what the 4-pole motor is about. The 4-pole motor is the best design without compromise, really. So you can increase the pole counts, but it starts becoming much more difficult. And the way that you solve that is to start winding it around laminations, which then introduces cogging, etc., which starts defeating the whole purpose of what you want from a Maxon motor. Okay.
And this one, are there certain industries or applications that only use 4-pole motors?
I mean, 4-pole motors are typically found in aerospace and medical application, but there's one industry, the downhole tool industry, where the sort of extremes of temperature and vibration, etc., they only use the 4-pole motors, which are Maxon's HD or heavy duty motor range. They're all 4-pole. So the oil and gas industry typically uses 4-pole motors.
Okay. Right. As I said, well, that is all the questions we have time for. But as I said earlier, the any questions that the audience has sent in that we haven't been able to answer, I will hand on to Maxon, and they will answer them for you offline. But with that, it really just remains for me to thank you, Matt, and to thank our audience for joining us. Thank you very much.